Hello, everyone. This is Gurumurthy Ramachandran, Ram, again, and we are going to be continuing today with our discussion of mathematical models for exposure assessment. Last time, we were in the middle of discussing the well-mixed room model, and we are going to pick up where we left off. So just to summarize where we had left off, we had discussed the processes that would cause a gain in the mass of the contaminant in the room air and processes that would cause a loss of the contaminant from the room air. This is just a repeat slide from the previous lecture, but it's a good place to start today. So the gain terms are there is an in-room source which has a strength of G milligrams per minute that is adding contaminant to the room air. The supply air, for the sake of generality, we are going to assume is also contaminated with the same contaminant, and the air supply is coming into the room at a rate of Q cubic meters per minute, and it has a concentration of the contaminant of Cn milligrams per cubic meter. So the supply air is adding the product of these two terms, Cn and Q, and the units of these are the same as the first term, so the units are milligrams per minute. Then we come to the loss terms. So the main process by which the contaminant is removed from the room air is the exhaust air. So just as in the supply air, now we have a different concentration, which is the room concentration, C room, multiplied by the same flow rate, Q, in cubic meters per minute. So the product of these two has units of milligrams per minute, and this is the amount per minute of contaminant that is exhausted, removed from the room air. There are other mechanisms also that remove contaminant. These include phenomena such as adsorption of the contaminant molecules onto the walls and other surfaces, for example, carpets and furniture. And there could be chemical reactions that remove the contaminant. And in the case of particles, there could be mechanisms such as gravitational settling that also remove the contaminant from the room air. These are all combined into one loss rate, which is denoted by Ks of L in units of inverse minutes. And if you multiply that by the room concentration C room and the volume of the room, you again end up with a term which has units of milligrams per minute. Now we set up the mass balance equation, and you guys might have to dig far back into your calculus training, and this will come back to you. So the way we set it up is that we can consider a very small infinitesimal interval of time from t to t plus dt. And in that time instant, we account for all the contaminant mass entering the room air and that are removed from the room air. And so the change in the contaminant mass in this small interval is the mass gain minus the mass loss. And by equating the change in mass as the gain minus the loss, we say that mass is conserved. So very simply put, the change in mass in a time interval dt is the mass gain in the time interval dt minus the mass loss in the same interval dt. And the change in the mass in this time interval t to t plus dt must equal the product of the room volume, V, which has units of cubic meters, and the infinitesimal change in the concentration in the room air, denoted by dc, which has units of concentration, milligrams per cubic meter. And so we can say that the change in mass in dt is V times dc. And if you look at the units of this product, again, is the units of mass, or milligrams. So this notation leads to a mass balance equation. So the change in mass in dt is mass gain minus mass loss in that time interval. So the left-hand side, change in mass, is the product of the room volume V times the infinitesimal change in concentration dc. Now we move to the right-hand side. So the mass gain terms are, if you remember, the source that is adding contaminant as well as the contaminated supply air. So those are the first two terms. So the source has a strength of G, which has units of milligrams per minute, and then you multiply it by time, which has units of minutes. So the product of G and dt has units of milligrams or mass. The second term, which is Cn times Q, if you remember, that also has units of milligrams per minute, and then you multiply it by dt, so the units of the second term entirely is, again, mass, milligrams. Then we come to the mass loss terms, and so these are subtracted. So the first term among the mass loss, or the third term in the equation, is C room, which I've simplified here to just say C as a function of time, Ct, times Q times dt. So this is the mass loss from the room air because of the exhaust air. And then the last term is the loss due to all the other processes. So case of L times C as a function of time times the room volume times dt. So we have essentially accounted for all the mass. So the mass gain terms minus the mass loss terms is equal to the change in the mass in the room air. It's a simple accounting of the mass, but since we are using this accounting for an infinitesimal instant of time, this leads to what is known as a differential equation involving the unknown function C as a function of time, which is the room concentration, and its first derivative, which is the dc. And if we solve this differential equation, that would mean that we have specified the function C's of t, the time-varying function for the contaminant concentration in room air. Again, at the top, I have that equation from the previous slide, and we can divide both sides by V and dt, and we will end up with this equation. So on the left-hand side, we have dc over dt, which is the derivative of the concentration with respect to time, or change in concentration with respect to time. And we have the other terms on the right-hand side. We can do some algebraic arranging of the terms, and we basically collect all the terms that are associated with the concentration terms and then rearrange it. And so we get the equation at the very bottom of the slide. So dc over dt plus there is this q plus case of L times V divided by V, and this whole term is multiplied by the concentration. And on the right-hand side, we have all the terms are a constant, because if you recall, we are assuming that G, even though I'm denoting it here as a function of t, for the first exercise, we are going to assume a constant emission rate. So G is, in fact, constant. It doesn't change with time. And Cn is the incoming supply air concentration, and Q is a constant, and V is a constant. So the entire right-hand side is a constant. And on the left-hand side, we have the unknown concentration C and its first derivative dc over dt. And this is not a course in calculus, so I'm not going to go through the blow-by-blow of how this is solved, but we solve that differential equation, and I'm going to present the solution to you here in this equation. So if we assume that Cn, the concentration of the contaminant in the supply air, is greater than 0, and case of L is also greater than 0, then our solution comes out to be this equation. And rather than read out the entire equation to you, I'm going to point out some features. So the first term on the right-hand side is this ratio of two terms, and that's essentially a constant. So G plus Cn times Q divided by Q plus KL times V. So all those terms are constant. And this is multiplied by a term which looks like 1 minus exponent, or e to the power, again, a constant times t, or in fact, minus a constant times t. And so we have a second term which has a coefficient c sub 0, which is the contaminant concentration in the room at t equal to 0. And this is multiplied by an exponential decay term. So it's exponent e to the power minus some constant times t. For the sake of simplicity, what I'll do in the next few slides is we'll assume that the Cn is 0, which means there is no contaminant in the supply air, and case of L is 0, which means there are no other loss mechanisms other than the room exhaust. This doesn't mean that the previous equation cannot be useful. In fact, there are many instances where we need to use all those terms which we are setting to 0 here. But for our discussion here, it'll be a lot easier if we just use the main mechanisms that are adding and subtracting contaminants from the room air, which is the generation rate, G, and the exhaust flow rate, Q. So by eliminating Cn and case of L, we look at more clean-looking equation. So the first term on the right-hand side is G over Q multiplied by is 1 minus exponent minus Q over V times T. And the second term is C sub 0, which is the contaminant concentration at T equal to 0. And this is multiplied by exponent minus Q over V times T. So even though we can program this entire equation in Excel and look at how the concentration varies with time, it will be useful to spend a few minutes discussing this equation from a physical basis so we get a feel for what's happening physically in the room. Let's focus on the second term of this equation, the exponential decay term, and see how that changes with time. So when you have t equal to 0, then the first term, meaning G over Q multiplied by 1 minus exponent minus Q over V times T, that entire term vanishes because the exponential term is equal to 1, and you have 1 minus 1 equal to 0. The second term, which is an exponential decay, it starts off when t equal to 0, the exponential term is 1, and C sub 0, that is the concentration at t equal to 0. And as time progresses, that exponential decay term becomes smaller and smaller, so the second term essentially becomes 0 after some time. Now let's come to the first term, which has the coefficient G over Q. So when you start off at, again, time t equal to 0, the first term, which is 1 minus exponent minus Q over T, that is equal to 0. So we are starting off at the concentration contribution from the first term equal to 0. But as time progresses, the exponential part of it becomes smaller and smaller compared to 1. So 1 minus this exponential term becomes larger and larger. And so the concentration contribution due to this first term starts off at 0 and starts increasing. But it doesn't increase linearly and keep on increasing forever because this is an exponential decay term here too. So as time increases, the exponential term, which starts off at 1, it eventually also goes to 0. And so the highest concentration contribution due to this term is in fact just G over Q. So the maximum concentration that can be attained by the sum of the first term and the second term is in fact G over Q. So after sufficient time has passed, or T has become sufficiently large, the concentration doesn't become infinitely large. It reaches a value of G over Q and cannot increase beyond that.